In this video, we are going to look at structural isomers. There are three different types of structural isomers, and you must be able to distinguish between all of them. First of all, we need to know the definition very well. They are organic molecules which have the same molecular formula but different structural formula. I'm going to use the butane molecule to briefly explain what isomers are. The molecular formula for butane is C4H10. It is an alkane molecule with 4 carbon atoms and single bonds between the carbon atoms, therefore it's an alkane. It's called butane. The molecular formula of this molecule is C4H10. If I wanted to change this into another isomer, I would remove one of the carbons on the end and put it on the middle carbon, one of the middle carbons. We then form a chain of 3 carbons with a side branch of 1 carbon. This side branch is called a methyl side branch because it consists of 1 carbon, meth for 1 carbon. The longest chain is 3 carbons, so this is methyl propane, and it is an isomer of butane. It also has the formula C4H10. So you may want to pause the video and just check that. Count whether there are 4 carbons and 10 hydrogen atoms in the molecule as well. Next, we are going to look at the 3 different types of isomers. We get chain isomers, positional isomers, and functional isomers. I will be going through all 3 of these very carefully using examples. Just take note that they all fall under the main heading structural isomers. Firstly, we will be looking at chain isomers. These are isomers where the chain length differs. All these molecules will have the same molecular formula, but they will have different structural formulas. I'm going to give the structural formulas as complete structure, but also as condensed structure so that you can get used to seeing that as well. So first of all, we are using pentane, which is 5 carbon atoms and 12 hydrogen atoms in the molecule. The first basic pentane molecule is given above. I've also given it as a condensed structure. When you see CH2 in brackets with the number outside, it's just a shorter way of writing CH2, CH2, CH2. So make sure that you are familiar with that way of writing the molecules as well. So the first molecule is just our normal pentane. Pent, 5 carbon atoms in the chain, ane because there are single bonds between the carbon atoms. To form an isomer from straight chain pentane, I would take one of the carbons and put it on one of the middle carbons, not on the end, because if you just bend it down, you've just made a kink in your chain and it's still a chain of 5. So what you will then have is 4 carbons in your chain with a methyl group coming off one of the carbons. The name of this structure, this molecule, would be 2-methyl butane. 2-methyl, because the methyl is on carbon number 2, you would have to start numbering on the right hand side. So it's carbon number 1, carbon number 2. We start numbering on the right hand side because the methyl side chain is closer to the right hand side. The longest chain is 4 carbons, so it is 2-methyl butane. If this methyl group had been on that carbon, it would also be called 2-methyl butane because then you would start numbering on the left hand side. The condensed structure for this molecule, you just read it from left to right as it occurs in the normal structure, CH3, CH2, but now on the 3rd carbon from the left, we have an H and the methyl group, and then the last CH3. So that is the condensed structure for that second isomer of pentane. The third isomer of pentane is a chain of 3 carbons. You can count across like that, or from top to bottom, or even go at an angle. You will always find that you have 2 methyl groups on the middle carbon. The name is therefore 2,2-dimethyl propane. If I count the carbons, 1, 2, 3 from left to right, I have a methyl above and a methyl below. Therefore 2 methyls, the name is dimethyl propane. The name is 2,2-dimethyl propane because the methyl groups are both on the second carbon. Should you leave out the 2,2 and just call it dimethyl propane, the name would also be correct because they can only be on the second carbon. Now I would like to compare these 3 with regards to their boiling points. Just very briefly, I'll be doing another video on that. But the straight chain carbons, the straight chains have higher boiling points than the molecules that are more spherical. All 3 of these molecules have the same molecular formula, but you can clearly see they have different structural formula. The longer the chain, the stronger the van der Waals forces. They are non-polar molecules, so these are London van der Waals forces. The longer the chain, the stronger the London forces. The more spherical the molecule, the weaker the London forces. The weaker the force, the less energy is needed to break the bonds, therefore the lower the boiling points. So when we have chain isomers of a molecule, the longer chains will have higher boiling points. The shorter chains, the more spherical molecules, will have lower boiling points. So if the boiling point is lower, the molecules need less energy to evaporate. So this molecule will have a higher vapor pressure than the straight chain pentane molecule. Now we're going to look at positional isomers. Positional isomers have the same functional group and the same chain length, but the position of the functional group is going to change. The example that I'm using is chloropropane. 3 carbons, 7 hydrogens, and a chlorine. The chlorine is the halogen, so I am going to change the position of the halogen. In the first molecule, the chlorine is on the carbon on the left-hand side, so we will start numbering from the left-hand side. So it's on carbon number 1. So the name is 1-chloropropane. Chlorine atom on number 1, prop because there are 3 carbons in the chain, and ane because we have single bonds between the carbon atoms. In the second molecule, the chlorine is on the middle carbon. So in this one, it doesn't matter whether we number from the left or from the right, chlorine will be on carbon number 2. So the name is 2-chloropropane. I quickly want to mention the difference in boiling point in this example. Chlorine is on the end. It has a high electronegativity, so it will draw shared electrons towards itself. So this molecule will be slightly polar. In the second molecule, the chlorine is in the center, so it will be less polar. The more polar the molecule, the more the bonds will tend to be dipole-dipole van der Waals forces. So the dipole-dipole forces in this first example will be stronger than dipole-dipole forces in the second one. So the first one therefore has a higher boiling point than the 2-chloropropane. You can see in both these examples, the chain length is the same, 3 carbons in a chain, but the position of the functional group differs. In these 2 examples, we have exactly the same chain length, but the position of the chlorine atom is different. So therefore, they are called positional isomers. Another example of positional isomers, We're going to look at butene. Butene is a chain of 4 carbons with a double bond, therefore the name ends with -ene. The molecular formula is C4H8 for both of these molecules. But what we've done here is we've moved the position of the double bond. In the first molecule, the double bond comes after carbon number 1, so it's but-1-ene, or you can call it 1-butene. We will be numbering from the right-hand side. In the second one, but-2-ene or 2-butene, it doesn't matter from which side we start numbering. If we number 1, 2, the double bond comes after number 2. If we number from the right-hand side, 1, 2, the double bond comes after number 2. So therefore the name is 2-butene or but-2-ene. These are positional isomers because the position of the functional group has changed. They have different structures but the same molecular formula. We're going to look at one more example of positional isomers where we move the position of the functional group. Ketones and aldehydes will be positional isomers when they have the same number of carbon atoms. They have the same functional group, which is the carbonyl group, carbon with a double bond O. Now you know that your ketones have the carbonyl group, and so do your aldehydes. It's just the position that differs. When your double bond O is not on the end carbon, then it's a ketone. So I'm going to look at 2 examples of ketones. We'll come back to those. But if we look at this third one, the double bond O, the carbonyl group, is on the end carbon. That makes it an aldehyde. Aldehydes names end with -anal. For example, methanol, ethanol. In this case, we've got 5 carbons, so the name is pentanol. You don't need a number to indicate where the carbonyl group is, because in aldehydes it will always be on the end. We'll go back to our 2 ketone molecules. In the first one, the double bond O, the carbonyl group, is on carbon number 2. In this example, I have to start numbering on the right-hand side, closest to your functional group. So this is carbon number 1, there's carbon number 2. The carbonyl group is on number 2. So the name is pentane 2-one. Ketones end with O-N-E. You can also call this molecule 2-pentanone. The second ketone, the double bond O, the carbonyl group, is on the middle carbon. It is a symmetrical molecule, so it doesn't matter which side you start numbering. It will be on number 3, so it's pentane 3-one. These 2 molecules are ketones because your carbonyl is not on the end carbon. As I said before, this is pentanol because the double bond O, the carbonyl, is on the end carbon. So if it's on this carbon or that carbon, it would be pentanol. All 3 of these molecules have the same molecular formula, C5H10O. Pause the video to check. The next type of isomer that we will be looking at is the functional isomer. Functional isomers also have the same molecular formula and different structural formula. And the way the structure differs in this case is they have different functional groups. Therefore, they are called functional isomers. The examples that you will have are carboxylic acids and esters. They will be functional isomers if they have the same number of carbon atoms. The definition: functional isomers have the same molecular formula but different functional groups. We will look at pentanoic acid. Penta means 5, so there are 5 carbons with a carboxyl group always on the end carbon. The carboxyl group is the C double bond O OH. Always draw the OH with the O attached to the carbon, and the carboxyl group is always on the end carbon. So this is pentanoic acid. Carboxylic acids names end with oic acid. So on the left we have pentanoic acid. The formula is C5H10O2. If we write an ester molecule with 5 carbons, I have an example here. This is methyl butanoate. We also have 5 carbons, 10 hydrogens, and 2 oxygens. Carboxylic acids and esters that have the same number of carbons will always be isomers. They will be functional isomers because they have different functional groups. We are now going to look at a few examples where you are going to have to draw the structures of each molecule. In each example there are 3 different structures, and then at the end you have to compare the structures of A and B and B and C and say which type of isomers they are. So pause the video and draw the 3 structures for pentanol, pentane 2-one, and methyl butanone. We will check the answers in a while. Here are the structures for example 1. The first one, pentanol, is an aldehyde, so your carbonyl group is on the end carbon. Please be careful to not add an extra hydrogen onto the carbon which has the carbonyl group. In aldehydes and ketones, each carbon atom can only have 4 bonds. So this double bond O carbonyl group could be on the first carbon on the left hand side. It doesn't matter which end you put it on. The second one, pentane 2-one, your double bond O must be on carbon number 2, so our number from the left, 1, 2. Or it could be on the second one from the right, then you would number 1, 2. So we have an aldehyde, a ketone, and then we have a ketone with a side branch because it's methyl butanone. In this one, we'll start numbering on the left hand side because your carbonyl is closer to the left. So we have a methyl group on the 3rd carbon. You do not have to name it as 3-methyl butanone because the methyl group cannot be on any other carbon. Now we're going to compare A and B. A is an aldehyde, B is a ketone. The only difference here is the position of the carbonyl group. So they are positional isomers. Now we compare B and C. They are both ketones because the carbonyl group is not on the end, but the chain lengths differ. So B and C are chain isomers. Example 2. Draw the following structures again: butyl methanoate, methyl butanoate, and pentanoic acid. The first 2 are esters and C is a carboxylic acid. Then answer the 2 questions at the bottom. What type of isomers are they? Here is the structure for butyl methanoate. It's an ester. I'm not going to go into the synthesis of how esters are made, but very quickly, just to go over it. If it starts with butyl, the alcohol that was used was butanol. This single bond O came with these 4 carbons on the left. The alcohol gives the first part of the name. So all of this from the left to there is from the alcohol. So it was butanol reacting with methanoic acid. So the name is butyl methanoate. The second one, methyl butanoate, that would have come from methanol and butanoic acid. Both of these molecules have 5 carbon atoms. Pentanoic acid also has 5 carbon atoms, but it has a carboxyl group as a functional group, whereas the esters have the double bond O and the single bond O. So they have different functional groups. A and B have the same functional group, but the position differs. C has a completely different functional group. All three have the same molecular formula, C5H10O2. So A and B are positional isomers because the position of the ester functional group differs. And when we compare B and C, they have completely different functional groups. So B and C are functional isomers. We are going to look at another example using molecules with 5 carbons. Again, pentanoic acid, 3-methylbutanoic acid, and ethyl propanoate. Pause the video, draw your structures, and answer the 2 questions at the bottom. Here are the structures for example 3. All 3 have the same molecular formula written on the right hand side. I've given the structure for each one. The first one is just the straight chain pentanoic acid with your carboxyl group, because it's a carboxylic acid on the right hand side. In the previous example I drew it on the left hand side. B, 3-methylbutanoic acid. It's a carboxylic acid, so we must have a carboxyl group on the end, but it has a methyl on number 3. We have carbon number 3. We have to start numbering from the right hand side where our functional group is. 1, 2, 3. I've drawn the methyl with condensed structure just to make the sketch a bit clearer. So 3-methylbutanoic acid. This is the molecule. Same molecular formula but different structures. Then C, ethyl propanoate. That is an ester. All esters have a double name with something -yl, something anoate. In this case, ethyl propanoate means that it was made from ethanol and propanoic acid. Completely different functional group to the carboxyl group in the first 2. Now we have to compare A and B. A and B have the same functional group. They're both carboxylic acids because they both have a carboxyl group on the end, but the chain length differs, so they are chain isomers. When we compare A and C, pentanoic acid and ethyl propanoate, this is a carboxylic acid, this is an ester. They have completely different functional groups, so therefore they are functional isomers. For example number 4, you must draw 5 isomers for the molecular formula C6H12O. There's 1 oxygen, so these will be aldehydes and ketones. Pause the video, try to draw 5 isomers, and we will review in a while. Here are 5 structures for C6H12O. The first one that I have is hexanal. It is an aldehyde. The second one is hexan-2-one. My carbonyl is on carbon number 2, numbering from the right. The third one is hexan-3-one. I've just moved the position of the double bond O. It's on number 3 if I number from the right. Then I made 2 chain isomers with side branches. On the first one on the right hand side, I have a methyl on the second carbon. So this is an aldehyde because we have the carbonyl group on the end. Our longest chain is 1, 2, 3, 4, 5. So it's a pentanal with a methyl on number 2. So its name is 2-methylpentanal. Remember, aldehydes don't need numbers to show where the carbonyl group is. This is a ketone because my carbonyl group is not on the end. The longest chain is 1, 2, 3, 4, 5. So it's a pentanone with a carbonyl group on number 2. So it's pentan-2-one or 2-pentanone. But I still need to specify where my methyl group is. I have to number from the right hand side, closest to my carbonyl group. 1, 2, 3. The methyl is on carbon number 3. The name of this molecule is 3-methyl pentane 2-one or 3-methyl 2-pentanone. See if you can find more isomers for C6H12O.